Good morning, summer class, so geometry semester 1 students. So here's the pretest analysis for unit 3. So unit 3, it's all about analyzing the right triangles, special right triangles, and also the proof for the right triangle, and also their similar triangles, the proof for the similar triangles. So what kind of theorem that we need to apply for those kind of congruent triangles or similar triangles. So let's start it off with the Pythagorean theorem. So you guys may notice the Pythagorean theorem, it's about a squared plus b squared equals c squared. So for the first example here, so which of the following equation can be used to find the length of segment BC in the triangle below? So let's say we do have a right triangle, we do have the shortest leg, we do have the longer leg, we do have the longest leg. So the longest leg, it's always considered the hypotenuse. Again, hypotenuse, it's always called the longest leg. So A, which is the shortest leg, B, which is considered the longer leg, and then C, which is the longest leg. So the way to set up the Pythagorean theorem, it's about using a squared plus b squared equals c squared. So since we do know that A is 10, and then B, which is 30, so we just plug in the number, so 10 squared plus 30 squared, so that equals segment BC squared. So the correct solution for this one is B. So the next one is quite similar. So identifying the shortest leg, which is 12, and then longer leg, we don't know what that is. So another way to find that is by using the alternate form of the Pythagorean theorem. So one thing that we notice, so c squared minus a squared, so that equals b squared. So this case right here, so plug in a number, so we do have 24 squared minus 12 squared equals segment EF squared. So another way you can express this one is by using c squared. So c squared, which is 24 squared, and then minus a squared, which is 12 squared. So that equals EF, so which is b squared. Okay, so the next one is quite similar. So the other way to put in the Pythagorean theorem form, so that would be considered c squared minus a squared. So that equals b squared. So 1c is quite similar to 1b. And then what's the length of segment BC in the right triangle below? So this one is basically using the Pythagorean theorem. So a squared plus b squared equals c squared. So let's say that you want to show the word. So let me just highlight this problem here. Okay, so I just want to copy and paste the triangle. So it doesn't allow me to copy and paste the triangle. Here we go. So copy image, and let's just put it right here. Okay, so we do have segment, the shortest segments, the longer segments, and we need to find out the longest segment here. So going back to the problem, so the shortest segments, we do have 8, and then the longer segment, we do have 15. So this one will be considered a squared plus b squared equals c squared. Again, it's a right triangle, so we can apply the Pythagorean theorem. So keep that in mind. The only way that we can apply the Pythagorean theorem is that the given triangles must be a right triangle. If the given triangle is something other than a right triangle, so you're not allowed to use the Pythagorean theorem. Okay, so for A in this case, so we do have 8. So 8 quantity squared plus 15 quantity squared, so that equals c squared. So back to the solution, this one is just solving it all the way through. So a squared, which is 64, and 15 squared is 225. Combine them, so we do have, well, 4 plus 5 is 9, 6 plus 2 is 8, so 289 c squared. But another thing that you need to do is by taking the square root of this number. One thing that we notice, so let's see, let's going back to the selection, what we got here. So square root of 289, it is a perfect square number. So just take the perfect square number, so this one would be considered 17. Because 17 times 17, which is 289. Okay, so now let's move on to the next one. So the other one is quite similar, so a squared plus b squared equals c squared. But the thing is that 234, it's a non-perfect square number, so nothing we can do about it. So even you try to break it apart, perfect square number, non-perfect square number, but this one it's impossible. So we just leave the answer like that. And here's the third one. So a squared plus b squared equals c squared. So 175. So this one's a non-perfect square number. And according to what we normally do, so this one you can simplify it a little bit further. But according to the solution we have, we just want to leave that within the radical. So basically just keep that as square root of 175. Actually, it's 25. It's a perfect square number. So once you take the sum, it's going to be 625. So square root of 625, which is 25. Okay. And then for number 3a, so this one using the alternate form of the Pythagorean theorem. So let me just copy the image so I can do it on the Promethean Active Inspire. So for this one here, it's quite similar. Okay, let's just try that one more time. Copy image. And paste. So what we got here, we got 7, which is the shortest leg, and then the longest leg is 13. So using the alternate form of the Pythagorean theorem, so then that would be considered b squared. So that equals c squared minus a squared. Because one thing that we notice, a squared plus b squared equals c squared. If we try to convert the form algebraically, so we try to isolate that b squared, so we subtract a squared on both sides. So we do have b squared equals c squared minus a squared. So that's how I come up with the alternate form for the Pythagorean theorem. So according to what we know, so we do have 13, which is the longest leg. Shortest leg is 7. Okay, so let's just plug in a number. So b squared equals 13 squared minus 7 squared. And before we continue to work on the rest of this, let's check the solution first. So this one again. So for the final solution, you need to simplify it all the way through. So 13 squared, then that'll be considered 169. And then 7 squared is 49. So once you subtract, you'll get 120. And the thing is that in order to get rid of the exponent, so you want to take the square root both sides. So that means b equals square root of 120. Okay, so it's about the alternate form of the Pythagorean theorem. Okay, going back to this one here, so 3b, so it's quite similar. So c squared minus a squared equals b squared. So once you plug in a number there, try to evaluate it, simplify it all the way through, and then you end up with square root of 280. And then 3c is quite similar. So now what about for question 4 here? So question 4 looks like this one, it's not a right triangle, it's a scaling triangle. So which of the following statements justify why the triangle shown below it's not a right triangle? So in order to prove that's not a right triangle, so that means you want to show that a squared plus b squared cannot be c squared. Again, a squared plus b squared does not equal c squared. So the correct solution we have for this one here would be B, selection B. So this one showing that a squared plus b squared does not equal c squared. Okay, so for B, it's quite similar. So showing that 4 squared plus 12 squared cannot be 13 squared, or does not equal 13 squared. So for C, again, it's a scaling triangle, so all three sides are different. So that means you want to show that it's the non-right triangle. So we want to prove that a squared plus b squared cannot be c squared. And then question number 5, which definition best describes the Pythagorean triples? So anytime they see the keyword Pythagorean triple, so that means a, b, and c, those three numbers must be a whole integer, must be considered positive integer or a whole number. Okay. So set of three whole number a, b, and c that satisfy the equations of a squared plus b squared equals c squared. So answer D, that's correct. And here's another one. Okay, going too fast here, so let me go back. So 5b is quite similar, just ask you about, the name for the Pythagorean triple. So So which of the following is best described? A set of whole number A, B, and C that satisfy the equations. So this one, 5A, 5B, they're just considered like conditional statement and converse statement. Okay, so 5C, so quite similar. So it's about describing the Pythagorean triple. Again, all three numbers, A, B, and C, they're all considered positive integers. And then number 6. Which of the following is missing side length that complete the Pythagorean triple below? So this one, you can definitely using the Pythagorean theorem. So a squared plus b squared equals c squared, and then solve for c. And then by the time you solve for c, you'll get 13. Again, all three numbers must be a whole number or positive integers. So again, it's all about using the Pythagorean theorem, just like what we've been doing, the one for 1a all the way through 4c. Okay, so the Pythagorean, so this one you have to apply the alternate form of the Pythagorean theorem. Again, the final solution should be a whole number, because this one is identifying the Pythagorean triple. So 25 squared minus 7 squared, so 625 minus 49. And then once you take the square root of the difference, so you end up with 24. And then 3, 4, 5, so that's one of those Pythagorean triple. Not 1, 2, 3, because this one, it doesn't satisfy the Pythagorean theorem. 4, 5, 6, also that one, it doesn't satisfy a squared plus b squared equals c squared. If you plug in a number, both sides are different. Okay, so maybe we should try this one here. So, which of the following represents the length that form a Pythagorean triples? Again, whatever the number that you plug in that to the Pythagorean theorem, if that satisfies the entire equation, so that means all those three numbers should be considered the Pythagorean triple. And also make sure that those three numbers got to be a whole number, positive integers. And then question C, it's quite similar. It's about using the Pythagorean theorem. So one thing that we notice, the shortest leg, the longer leg, and we need to find out the length for the latter. So a squared, so which is a squared, and then plus b squared, 15 squared, and then combine them. So take the square root of the sum, and then you get 17. So again, it's all about using the same theorem over and over again. Word problem, this one too. So finding the length for the ramp. So a squared plus b squared equals c squared. So 5 squared plus 12 squared equals c squared. So it's 169, and then take the square root of 169, you'll get 13. Alright, so far so good, and it's all about the Pythagorean triples. Okay, so 6, 6, and, well, this one is 6, 8, and 10. We can use the Pythagorean theorem for this. Obviously, this one is 6, 8, 10, Pythagorean triple. And this one too, 9, 12, and 15. So the reason why that I do know that it's 9, 12, and 15, here's another shortcut you can do the Pythagorean triples. So one thing that we notice, so the small numbers for the Pythagorean triple, it's considered 3, 4, 5. So now what happens if I multiply each number by 2? So if I want to expand it 2 times of the original number, so we got 6. This one I got 8, and then the next one I got 10. So that's another set of the Pythagorean triple. So here's the first set. Here's the second set. So now what happens if I multiply this number by 3? So 3 times 3, then I got 9, and then 4 times 3, and then I got 12, and then 5 times 3, then I do have what? 15. So that's the third set. And they're all considered the Pythagorean triple. So we can always moving along that, so multiply by 2, multiply by 3, and then multiply by the next integer, which is what? 4. So 3 times 4, you get 12. 4 times 4, you get 16. 4 times 5, you get 20. And then multiply by 5, then you'll get 15. And then the next one, you'll get 20. And then 5 times 5, which is 25. So they're all considered the Pythagorean triple. Okay, so now let's see what else that we have for the rest of this. So that's AC, it's quite similar using the Pythagorean theorem. C squared minus A squared equals B squared, or using the Pythagorean triple. So it looks like this one, we actually have to multiply it by a larger number. Okay, so now the next one I would like to talk about here is the proof. So now, as you may notice, so this one is about the congruent triangles, but it's a congruent triangles of a pair of right triangles. Okay, so that's proving the congruent triangles of a pair of right triangles. So that means we do have such postulates. We do have HL, which is considered hypotenuse and leg. Again, hypotenuse, which is the longest leg of the triangle. And then also this one can be proved by leg. Okay, so let's say the shortest leg is given, the longer leg is given. So we can compare that if they do have the exact identical length. So we can use that LL or double L's. And also this one can be proved by hypotenuse and angle. Okay, we'll talk about that later. And also if that's a congruent right triangle, it also can be proved by leg and angle. So according to the figure here, so the tick mark, this one is showing that it's hypotenuse and leg. You see that hypotenuse is being indicated with the double R, the double segments or the double mark. So that means this one can be proved by hypotenuse and leg. So the correct solution is HL, hypotenuse and leg. So here's another examples, hypotenuse and leg, hypotenuse and leg. And now what about this case right here? Again, it's a right triangle, so hypotenuse, it's not indicated here, but we do have two legs are being indicated. So you might be wondering, can this one be proved by psi angle psi? Yes, it can be proved by psi angle psi, but somehow, the selection is not listed with psi angle psi. So another alternate proof for this one is considered leg, 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 or double legs. So here's another example, so which can be proved by psi angle psi, but the thing is that it's a right triangles. So here's another right triangle. So this one can be done with the proof by using leg, leg, or double legs. So here's another example for leg, leg. Now what about the other pair of two right triangle here? So this one we do have angle and then the hypotenuse. So for those you might be wondering, can we prove this one by angle, angle psi, angle, angle psi? Yes, indeed, this one can be proved by angle, angle psi, but we're not using angle, angle psi, and also it's not on the list. So in another way to prove the right triangle congruency is by using hypotenuse and angle. Hypotenuse and angle. Okay? So here's another examples for the hypotenuse and angle. Make sure that the hypotenuse and the angle, they're right next to each other. So hypotenuse and angle. So what about the example like this? Hypotenuse and angle, once again. And here's another way to prove the right triangle's congruency. So this one is considered leg and angle. And a lot of people might be wondering, can this one be proved by using angle, angle psi? Yes. But the thing is that it's angle, it's leg and angle. Leg and angle. There's no such thing for angle leg, okay? So a lot of people might be wondering, can we prove this one by angle leg? No, this one, it started with the leg first. So it's leg, angle. Because they're considered corresponding to each other. So here's another examples, leg and angle. Because they're both considered right triangles. Cannot be hypotenuse and leg because hypotenuse, there's no any indicator on the hypotenuse. It cannot be leg, leg because we only have one leg with the tick mark. And then hypotenuse and angle. So again, hypotenuse, it's not given. We don't know anything about the hypotenuse. And the next one, quite similar. So again, leg and angle. Leg and angle. And the angle that we refer to, it's not the right angle. It's actually the normal acute angle. So another way to prove the right triangle congruency is by using the normal postulates such as psi, psi, psi angle psi, angle, or angle, angle psi. So this one with three psi's given. This one here, I think there's a little typo. Oh, you know what? This one is also showing that according to the diagram below, triangle LMK is congruent to triangle XYZ by hypotenuse and leg. If the Pythagorean theorem is used to show that segment LK, so let's just read through the instruction first. Segment LK is congruent to segment XZ. So congruence can be also shown by which of the following statement or the theorem. So this one, since we do know that LK is also the same as XZ, so for those two line segments, so that means this one can be proved by using psi, psi, and psi. So you probably want to put like triple tick mark here, so showing that they're both considered congruent. Okay, so psi, psi, psi. So here's another example. But this one would be considered, again, it's all depending on things that's given. We know that angle C is congruent to angle Z. So this one, the right angle, so it's also given. So that means this one can be proved by using psi, angle, psi. Psi, angle, psi. Again, anytime that you want to identify the theorem, the postulates for the proof, make sure that you need to read through the instructions and find out things that's given. And also we need to compare all the rest of the solutions we have here. Obviously, cannot be psi, 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 because that's the hypotenuse. We don't know anything about the hypotenuse. Cannot be hypotenuse and leg. Again, hypotenuse, we don't know anything about it. Hypotenuse and angle. So angle, there's only one pair of right angle. We're not quite sure about the acute angle here. So here's another one. So another way to prove the congruent triangles is by using angle, angle, psi. Okay, so let's just read through the diagram. So angle, angle, and psi. Angle, angle, psi. Or another way to read it, right angle started with the right angle first. Angle, angle, psi. And here's another one. Angle, angle, psi. So for number 14, it's a little bit different. So BD, it's perpendicular bisector of segment AC. So BD right here. So bisecting line segment AC. So here's the key word, bisects. So bisects, that means the line segment is actually the line of symmetry. It cuts off this base line segment here into half. So what's the length of segment AC? So DC is 6. So that means the other half is also 6. And then 6 plus 6, then that'll be 12. So here's another one. So again, this line segment, YS, is the bisector. It's the perpendicular bisector of XZ. So what's the length of XS? So half of 18, then that'll be 9. Okay, so this one is quite similar to that 14a. So half of it is 10. So what's the measure of the entire segments of the base? So 10 plus 10, 20. So again, let's just read through the instructions. So segment BD is the perpendicular bisector of triangle ABC, and BD is a shared size of triangle ABD and CBD. So by the reflexive property, so this one is called the shared size of those two right triangles. And which of the following must be congruent in order to verify the triangle ABD? It's congruent to triangle CBD. So since we do know that this one is by using reflexive properties, so they both share with this line segment in common, we do have the right angle. So here's another thing that to show the triangle congruent. So we can state that AD is congruent to CD. Okay, so AD is congruent to CD. Because this one can be proved by using psi, angle, psi. Psi, angle, psi. So the third information that we need here, it's AD. It's congruent to CD. So here's another one. So since we do know that this one is the shared size, so we do have a pair of shared size, and also we do have the right angle. So the third information that we need to show the triangle congruent is by using XS. It's congruent to ZS. So choice C. So 15, that one is quite similar, so we're not going to spend time for this one here. So now what about 16? So 16, which one of the following is the measure of angle Pzr? So anytime they see the perpendicular segments from the ray to another ray, from one ray to another ray. So it shows the perpendicular segment. So that means this angle here, this line here, this ray, it's called the angle bisector. So since we do know this one is the angle bisector, so half of the angle is 38. So that means the measure of this whole angle here, Pzr, then that would be considered 38 plus 38. So 38 plus 38, which is 76. Again, how do I know this one is considered the angle bisector? Because that it shows the ray, which is perpendicular to each other. Okay, so from one ray to another ray. From one ray to another ray, it shows the perpendicular line segment. So that's why the center ray, it's called the angle bisector. So here's another one, so quite similar. So what's the measure of angle RCP? So here's RCP. So the measure of the entire angle, so half of it is 33. So that means the entire angle would be considered 66. Either you can add 33 plus 33, or you can just do the multiplication, 33 times 2. Okay, so another one is quite similar, so we're not going to spend time for that one. And now, what about proving the similar right triangles? So the way to prove the similar right triangle, we can use either angle, or we can use side angle side, or we can use the postulate side. So if that's angle, that means it's showing that two pairs of angles are congruent. So this one is showing those two pair of angles are congruent. One is 90, the other one is 31. So it's angle. So here's another case. So angle. Okay, so angle again. The reason why they're similar, because that one is larger, the other one is smaller, and they're not exactly as the congruent triangle. Again, got to be careful with the congruent triangle. Congruent triangle, that means they do have the exact same length, same measurements, same size, same directions, and then the same area. But for the similar triangle, the angle can be exactly the same, but the side length, so one is longer and the other one is shorter. Okay, so here's another examples for angle. Angle again, 50. Well, this one is 50, that means the third angle would be 40. By using the triangle sum theorem, 180 minus 90 minus 50, you'll get angle D, which is 40. This one too, you'll get angle Y, 50. So 40, 40, 50, 50, 90, 90. So one is smaller, the other one is larger, so that means they're considered similar triangle, or similar right triangles. Okay, so the next one, angle again. So now let's talk about the geometric means, okay? So geometric means, so here's one of the examples. So what's the value of x in the figure below? So this one is about the comparison of all three similar right triangles. And if you take a look at the diagram here, we do have three similar right triangles. So one is considered ADB, the smallest one. And the medium right triangle would be considered ACD. So this one, the way that's lined up here, it's on the sideway. And then the largest one would be considered triangles BAC. There's a couple ways that I can do it. You can just reset the right triangle, or you can use the geometric means. So for this class, I'm going to show you the easiest way. It's about using the geometric means. Okay, so now let me just highlight this diagram. Once again, I need to save it. Okay, copy image. Okay, so keep that in mind. We do have 4, 12, and x. Okay, so using the Promethean board slide or the Active Inspire. Okay, so once again, so this one we do have 4, 12, and here's what we need to find out, x. So now, as you can see that this one here, so that's a small right triangle, so this one is the medium one. So just reset the figure, so we do have a small, medium, and a large one. Again, they're all considered similar triangle. So the reason why that I resketched them, I just want to show you the setup. Again, the small one, the medium one, and the large one, so they're all similar. So according to the first one, the smallest triangle, so this one is considered 4, and then the height, which is x. And then for the medium triangle, so make sure that you need to turn this one around back to the normal way. So the base for the right triangle, the medium one, then that would be considered x. And then the height here, then that would be considered 12. So just by comparing the small and the medium right triangles, so we can set up the proportionality statements or the proportionality equation. So this one comparisons the shortest leg versus the shortest leg and the longer leg the longer leg versus the longer leg. So we do have 4 over x, so that equals x over 12. Again, the shortest versus the shortest, and then the longer one versus the longer one. And then what we can do here, we can cross multiply them. Again, anytime they set up the same variable with the square, so that means it's called a geometric mean. Okay, so geometric mean. So it's about the comparison of the ratios. So once you compare the ratio, you can set up the proportionality statement, and that's what we need for the geometric mean. And you always see that it's a variable quantity square. So 4 times 12, then that would be considered 48. And then you take the square root of 48. Well, let's go back to the selection we have right here, because sometimes, it looks like apex. It doesn't simplify the answer all the way through. Okay, so for number 19A, so what's the value of x in the figure below? If necessary, round the answer to the nearest 10 of a unit. Oh, so this one, they actually simplified it all the way through. So basically, you can use the calculator for this. Now, what happens if you don't have a calculator for this type of problem? Another way you can do it, you can always separate it. So we can break it apart into a perfect square number and a non-perfect square number. So 48 would be considered 16 and 3. So square root of 16, which is 4. Root 3, we don't know what that is because that's the prime number, 3. So we just come up with the perfect square number and the non-perfect square number. If you try to do that on the graphing calculator or the scientific calculator, you'll end up with 6.9. If that's what the solution is given here. And now let's move on to the next one. The next one is quite similar. So this one is just 4 over x. So that equals x over 15. And then you just solve for x. Then you'll get 7.7. And then 19c is quite similar. So 7 over x equals x over 13. And then cross multiply, solve for x. And then you'll end up with 9.5. Now, what happened with the problem like this? So it looks like this one, it's another geometric mean problem. Once again, just want to highlight the figure, copy the image, and just want to do that on the new slide here. So once again, it's about the comparison of the shortest leg with the shortest leg, and then the longer leg versus the longer leg. It's hard to see those numbers, so I need to go back to this one here. So we do have x, and then the whole bottom base here is 20, and this one is 12. Okay, so let me just label it. So we do have x. The whole bottom base here, so that's 20, and this one is 12. So just want to make sure that this one, that's correct. So now, the way to set up the geometric means. So now let's just set up the right triangle. We do have a small one. We do have a medium one. And we do have the largest one, which is the whole triangle here. So the small one, as you can see that this one, the bottom base is x. Hypotenuse is 12. And then the medium one, we don't know the base, but we do know the height. Okay, so the height, which is considered the height right here, then that'll be considered 20 minus x. If you just subtract, it's using the segment subtraction postulates. And now let's see what else that we know regarding the medium triangle. That's all we know. And then what about the largest triangle, the whole triangle here? So the bottom base would be considered 12. And then the hypotenuse, which is 20. So instead of comparing the small triangle with the medium one, we want to compare the small triangle with the large size triangle here. Well, the reason why that is because that we do know the base, we do know the hypotenuse, so we can set up the proportionality ratio. So this one can be done by using geometric mean again. So it's x over 12, or x over 12, the shortest leg versus the shortest leg, and then the longest leg versus the longest leg. So 12 over 20. So 12 times 12, so you'll get 144. And then 20 times x, you'll get 20x. And then once you divide it, so this one, let's see what the answer is right here. So it's about 7.2. Well, it's exactly 7.2 with a decimal point. Okay. And now let's see what else that we have. So 20b is quite similar. So this one can be done by using the geometric mean. And as you can see, that's 17. We're not just using it for the small triangle, but also we're using 17 for the large triangle here. What I mean by the large size triangle is the whole thing here, ACB, or triangle ABC. So again, 17 is not just representing the hypotenuse of the small triangle, but also is considered the base. It's the base of the right triangle here, the large right triangle here. So that's why we can set up the proportionality, 17 over x. So that equals 24 over 17. So here's another one. So 14 over x, so that equals 30 over 14. So now, what about 21? So 21, that's quite similar to the one that we did earlier. As you can see, that m here, it's not just considered the hypotenuse of the small triangle, but this one, the hypotenuse for the small triangle, it's also considered the base of the large right triangle here. So the proportionality equation can be done by using 3 over m. So that equals m over 20. Okay, so now let's do this on the Active Inspire. So copy image. So we got 3, 12, and m. Okay, so copy and paste. So once again, let me just relabel this. So we got 3, which is the shortest leg of the base of a triangle here. And this one, I believe, is 12, but let me just double check this one here, making sure that, yeah, it is. So the other part of the base of this medium triangle, so this one is 12. And then over here, that's m. So just redraw the figure. So this one, just separate them. So we do have a small triangle, small right triangle, and then the medium one, and then obviously the largest one. They're all considered right triangle. So for the small right triangle, we do have the base, which is what, 3. Hypotenuse, it's m. And then for the medium triangle, the only thing that we know about the medium triangles, which is the height, 12. The base we don't know, the hypotenuse we don't know. And then for the large triangle, which is considered, well, 12 plus 3, then that'll be considered the hypotenuse, because that once you combine them, that'll be the measure of the entire segment, so then that'll be 15. Again, the way that I end up with 15, because that's 12 plus 3. And then the base of the large triangle, so which is considered m. And then the height, we don't know. Again, with all the comparison, the given information we have. So we want to compare the first triangle and the third triangle, the small one versus the large one. Again, so it's the smallest, okay, the shortest leg versus the shortest leg, so 3 over m. And then the longest leg versus the longest leg, so m over 15. And then from here, cross multiply, so we do have m squared equals 3 times 15, so 45. Again, as you can see, that it's a geometric mean, because we just square the same variable. So now, what we need to do here, so take the square root, so square root of 45. Again, the calculator, it doesn't do anything like factor tree. So you want to put it into the calculator and find out exactly what that is. And here's what we found. It's 6.7. So it's about 6.7. Not exactly, but it's about. Because that root 45, it's an irrational number. Okay, so now let's see what else for the rest of the pretest analysis. So that's 21. So 21b, it's quite similar. So you guys can try this one. So 7 over m equals m over 25. Again, you need to combine these two bases together to get the hypotenuse of the largest triangle. So once again, 7 over m equals m over 25. And then cross multiply, solve for m, 13.2. So this one too. So 4 over m, so that equals m over 17. And then solve for m, you got 8.2. And this one is something that we did earlier. So this one is also using the geometric mean again. So as you can see, that is, we do have 3 similar right triangles. The small one, the medium one, and then the largest one. So it's all about using 7 over h. So equals h over, well, this one you need to subtract. So 24 minus 7. You know what, let's just do this one for the last one of this pretest. Okay, so once again, copy and paste. Making sure that we're getting the right number. So we got 7, 24 for the whole bottom base here, and then the height, h. Okay, so let me just resketch this or label it. So this one, 7. And then the whole segment here, which is that 21 or 24? 24. And the height, that's what we need to find out. Again, if you just find the measure of the segment here, so this major segment, then that'll be considered 24 minus 7. So 24 minus 7, you'll get 17. So again, using the geometric mean, so we compare the small triangle and the medium triangles. So 7 over h, so that equals h over 17. Again, h is right along the small triangle here, and also is right along the medium triangle. So we have to use that variable or the element twice. So 7 times 17, so not quite sure what that is. You can always do it manually. I can do that on the calculator. So 1 times 7 plus 4, so 119. So that equals h squared. And then square root, again, this one is a non-perfect square number, so you have to use a calculator for this. It's irrational. So let's see what we found. So it's about 10.9. So now what happened for those who do not have a scientific calculator? So how do you come up with that number? So here's what you can do. You can find out the perfect square number, which is close by 119. So the higher perfect square number would be considered, okay, let's see what we found here. The higher perfect square number would be considered 121. And the lower perfect square number, which is less than square root of 119, then that'll be considered square root of, 100. So square root of 100 is a perfect square number, so that's 10. This one is 11. So that's why this number is bounded right between 10 and 11. So according to the selection we found here, so the one that's right between 10 and 11, so there's only one selection, which is 10.9. So here's another one. So just want you to be aware of that. This one, in order to apply the base, you need to subtract 18 by 5, or subtract 5 from 18. So you get 13. So h over 13, so that equals 5 over h. And then cross multiply, so h, which is 8.1. So word problem, so this one you can always set up the diagram and then so try to solve for the missing segments. Okay, so a cell phone tower casts an 80-foot shadow at the same time, and a 6-foot fence post casts a shadow of 4 feet. So what's the height of the tower? Okay, so basically this one is just about the comparisons of the triangles. So we can always set up the triangle here and try to come up with the missing segments.